Hi there, this is Matt Heffernan. Welcome back to the Retro Desk. And today we're going to revisit one of our more popular series, the 8-Bit Battle Royale. And today we're going to take a look at the Commander X16 and the Agon Light and do a head-to-head hardware challenge. Now that I have both systems in the silicon flesh, as it were, we're going to see what it looks like when the two are running up against each other, trying to do the Mandelbrot set plot. And of course, this is the very basic one. In fact, it's written in BASIC and then, of course, written in assembly to make it even faster. And this is based on that lowest common denominator capability of the original Sinclair ZX Spectrum. So let's take a quick look back at where things were when we left off. So for BASIC, the Commander X16 was faster than any of these other 8-bit CPU-based systems. And even the Sinclair ZX Spectrum Next, and that's a FPGA-based system. It doesn't have a fixed silicon 8-bit processor on it. It's taking the Z80 and making it run up to 8 times faster than that. It doesn't quite get as fast because of the slowness that is inherent to Sinclair Basic. But of course, you could optimize that too. But for the purposes of the proper 8-bit Battle Royale, we're talking about 8-bit computers that have actual physical 8-bit processors in them. And so the Commander 16, of course, is going to be a lot faster because it has an 8 megahertz 65 CO2. It's already a very efficient CPU, and running it at a clock rate that was unimaginable back in the 80s, of course, is going to make it a lot faster than even the top of the classic list, which was the BBC Micro. Well, of course, now we have the Agon Light, which implements BBC Basic in a much faster and more efficient way by using one of the newer 8-bit processors, and by new I mean released in the year 2000, the Easy 80 from Zilog. And so we're going to take a look at what we can do in BASIC and assembly. So meanwhile, for assembly, we don't have as many different platforms in here, but we got the times down significantly by doing assembly language on these systems, getting it down to just 3.2 seconds for the Commander X16 and 12.7 seconds for the BBC Micro. So definitely a big performance savings when you're not using BASIC. And you can even see down at the Commodore versus Sinclair, even though they're not as fast as some of these faster contemporaries, that the Sinclair ZX Spectrum having a 3.5 megahertz Z80 is still faster than the 1 megahertz Commodore 64 once we get closer to bare metal and we're not dealing with the inefficiencies of Sinclair Basic. So let's go now to our computers. All right, here we are. We have the Agon Light over here. And this is in this nice little custom-made case. And I've got the Commander X16 over here in a not-so-custom case. That is, of course, a repurposed case. And you can see a video on my channel about how I took this old PC case and repurposed it for using with the Commander X16. And of course, this is the first generation Commander X16 board. These are currently being manufactured and being sold to the folks who were the early backers of the product, and then going into the open market very soon. Those things are actually rolling off the line as we speak, and of course they're going to get this initial development version where it has all the expansion ports and the ability to upgrade it to 2 megabytes of memory like I have it here. And you can have then the full experience of the through-hole 8-bit dream computer from David Murray, the 8-bit guy. So whether your dream is to create something like the Commander X16 with all the through-hole stuff, or something a little more modern and small, like the VGA32, TTGO ESP32 board, you can get all of this done at PCBWay.com. PCBWay are the sponsors of the Retro Desk, and they can create a custom PCB for you and roll them off the line in their manufacturing space. But of course, they do a lot more. They do machining, they do 3D printing. If you're not so good at the surface mount technology, you can have them actually populate the board for you and drop the bill of materials and everything you need to make your own dream project a reality. So go visit PCBWay.com. Now let's get to the head-to-head matchup. First, we're going to do basic because it takes a little longer. And so we're going to see how these machines actually operate with BASIC. Now, we've seen the Commander X16 do this many times, but what we're going to do is use the built-in DOS to go into a special directory called mand. And then another DOS command to view the directory is this. So I've got a few versions of the benchmark here, but I am going to load up the basic one. And so I'll do, like as always, manbas.prg, load that up, and then I'll do a list. So there is the original BASIC program. This is what I wrote for the very first episode of the 8-Bit Battle Royale. And what I have now over here for the Agon is something similar. And the Agon also has a operating system, MOS, and I can get those calls instead of having to do DOS and the quote mark. It's a little easier. I can just do an asterisk and have it come up. So I can do cd mand and do a directory. And now I have all this stuff here for the 8-Bit Battle Royale. But what I'm going to do is load up the M2 print, and that is going to get me what I need. Now, I don't need to do the .bbc or .bas. You can load a text basic file, which is a really nice thing about this BBC Basic. But if I don't specify the extension, it will load the binary version .bbc, and that, of course, is generally going to be quite a bit faster. But this is a small program anyway, so it doesn't really matter. And there it is. You can see very similar. The BBC Basic does do the nice thing of indenting for you. And so there we go. Two almost identical basic programs, slightly formatted differently, but we can see that in the Commander X16 version, we have this vpoke statement. That's what's actually putting a character into the video RAM. And for the Agon, what you have is these VDU commands. So we do a VDU command to create a custom character that is just all the pixels set. You don't have the same sort of graphical character set like you get with a Commodore-like machine like the X16. So I create a fully solid 8x8 square, and that's going to be character 255. And then I can just do a print of that character. I don't have to do the VDU call to actually put that in there because I'm just going to be printing characters right through there, and that seems to be the most efficient way to deal with things with the Agon. So now that we have them both loaded, we can just type run and do our enters side by side. And now we see real hardware going head to head like this. So you can see a pregnant pause at the beginning for the Agon. You get to see this stuff getting updated immediately with the X16, but obviously the Agon catches up because here we are running a EZ80 at 18 megahertz running obviously the superior version of BASIC in BBC Basic, very efficient. But yeah, so now X16 is finally finished, and we're getting that similar sort of time that we saw on the emulator. The emulator is cycle accurate for the most part, and that's what we're still seeing here is this sort of 23-second performance from the X16. But over here on the Agon, we're seeing a 6-second performance. So that's pretty cool. Now, let's take a look at what it takes to make this happen in assembly language. Now, we've seen for the Commander X16, you can go back to the 8-Bit Battle Royale episode where I first introduced the assembly language version, and that's still the same version that's running over here. But what kind of extra performance can we get out of the Agon? Let's go look at the code. All right, well, if you saw my previous episode where I do the hello world for the Agon, you're going to see a very similar beginning to the code, and we are assuming ADL 1 for the code. Now, this is, in this case, we are going to show two different ways of doing it. The first is going to be actually using the Z80 compatibility mode, because we want to try to use the code as it existed for the other Z80 machines, like the Amstrad CPC and the ZX Spectrum. So, but first we need to, we're entering in from the MOS operating system into ADL mode, which means we have 24-bit addressing, and so we're going to have our program start at that 04 page right at the very beginning. And of course, we got to do the header here so that at the 64th byte, we're going to see MOS and then a 01, and then we can actually have the code. And so we have this space before that to do a little snippet of code to get us started. And so we just do a single jump to the start. We keep all our registers up there, and then we get to what we actually need to do. So first, we're going to set up our display in a similar way that we did in BASIC, where we just put us into mode 2, which gives us the color graphics and the nice big chunky characters, and then we also want to create that solid block character. And so to do that, we do this thing like we did for Hello World using that restart hex 18, and that will send a bunch of bytes through that serial link to the ESP32 running the VDP processor. And if we take a look at what it's sending here, it's a couple of commands. The first is to set to mode 2, and then creating that block, very similar to what we had in BASIC. And so we're just doing that in assembly. And then what we need to do is shift gears and get us back to Z80 compatibility mode. So we need to do a couple things first. What we need to do is set the MBase. Now we can see up here our MBase is the first 8 bits of this 24-bit address, because once we get to Z80 compatibility mode, we're only going to have this lower 16 bits of the actual physical address to deal with at a time. And so the MBase is going to be this up here, in this case 4. So we need to put 4 in the MBase register. And so you can see for the Easy 80, we have this new instruction to load a value from an 8-bit value from the accumulator into MBase. And so we're going to put 4 there. That'll keep us in this same part of memory. And then we do a special call, the call.lis, to this function we're calling plot. So call.lis means that, all right, we are in ADL mode, we're in long mode, and then we're going to make a call into Z80 compatibility mode, and that is, of course, short addressing. So we're calling from long to short, and this takes care of all the craziness that has to happen on the stack to be able to go back and forth between these two different modes. And so that will get us there. And then at the end, we have a little bit of cleanup. This doesn't quite actually work, but we're not really concerned about this, because once this call returns, that's basically when we're done doing the plot, and the rest of it doesn't really matter. So let's now see what happens at plot. Well, plot, here you can see we're doing an inc bin, which is a binary include. We're not including assembly code, we're including machine code and data right here. So the reason we're doing that is that our assembler that I showed you on the last video, Easy80 ASM, it can't do both modes at the same time. So it's either each file that you build has to be either for ADL or non-ADL ZD compatibility mode. So that's what we're going to do. But to make things a little easier, we're going to say, all right, we're going to start the Z80 code way up at 041000. So that then when we get to this code, it's going to be thinking, of course, that it's in just regular 16-bit address space. So it starts at 1000 hex. But it's really starting at 41,000 hex. So yeah, a little bit of trickery, but then that gets us into code that is purely 8-bit, 16-bit addressing Z80 code. And so that's over here. Now you can see at the top we're saying, yep, we're assuming ADL is 0, that we are in Z80 compatibility mode, and that we're starting at hex 1000 as our address, but of course, really 41,000. But the code in Z80 mode is no more aware of where it is really in memory. It's just given this 64K page to play around in, and then eventually it can hop back out. So then here everything else is pretty much the same, but you'll see we have to do a few things a little more explicitly, like when we're calling these restart vectors. These are actually in ADL codes. So what we have is the ability in Z80 compatibility mode to actually do non-Z80 stuff, like use the special opcodes for accessing ADL code using a restart vector like here. But then eventually we just return as we would from any Z80 code, and that'll get us back to the good old Easy80 ADL mode. So yeah, otherwise this code is very similar to what we would see in a Z80, except it has all these restarts. But it's also similarly to the ZX Spectrum, that it uses the restart 10 hex to actually output characters. And in this case, instead of outputting it to the ULA, it's outputting it to the VDP process running on that ESP32 on the other side of a serial link. So a little different mechanics under there, but ultimately it works the same. You're just sending characters out there, and yeah, so it works. And then we are including this as source code. As you can see down here, it's not an inc bin, it's an include. And here is that Z80, the same exact code that we've been seeing all along here. So this did not need to be modified for the Agon compared to the other Z80 machines, with the exception of a little bit of the special syntax for Easy80 as compared to other Z80 compilers and assemblers. So you can see here you have ats instead of dots for the local labels. So just a few little things like that had to be changed. And so then to build it, we were able to just do a couple of Easy80 ASM calls. So first we got to build the Z80 code, which we do here, and that'll give us this binary, the Agon Z80 Mandelbrot.bin. And that is, as we remember over here, we are doing the inc bin into our Easy80 ADL code over here. And so that will then get built into mz80.bin. And then you can see down here we're doing measy80 also. So this is the Easy80 ADL version, and we don't have to do the whole runaround of having to build some of the library codes separately, because it's a different instruction set architecture on the same CPU. We can just do it all at once and include everything. And so here we'll see it looks very much the same. Still Z80 mode, but we're doing a little thing differently here. we are doing a call.l to the plot method. And actually, we don't even need this. I don't know why I still have that there. So, yeah, we don't actually need to do this because we're going to be calling plot, and it's already going to be a 24-bit address, so we don't need to set the mbase there. But otherwise, we're doing the same sort of setup with the VDU, and then here we have the include of the assembly code rather than the built binary. So we don't have all that wasted space in between the main part of the code and this library. So once we get here, things are looking still fairly similar, but we do have the assume ADL1 up there, even though we're not building it on its own. But this is ADL code because then we're going to be doing things like return long, and we're calling manget, this library method, with a long call, and just making sure that we are staying in ADL mode all the time. And so then you can see here we're including this easy80 Mandelbrot.asm, and here we can see things are a little different. If you remember up here, we had these words, these 16-bit words for each of these variables. Well, the problem is in ADL mode, we're going to be loading things as 24-bit. So we got to put in some extra bytes so that we're not like doing any sort of weird corruption. So we can load 24 bits and ignore that upper 8 bits. They're just taking up space. And then you can see here we're calling, doing call.ls to fp divide, fp multiply. That's in our floating point library. And we're, again, staying in ADL mode, but you'll see a bunch of .s's here because we're dealing with these larger registers, which are no longer 16-bit, they're 24-bit, like HL, DE, BC. These are all 24-bit registers in ADL mode, but we still need to deal with them. We need to sort of chop them off at 16-bit, otherwise things go off the rails. So we kind of have to cheat a bit and say, all right, we're doing push.s just to keep the code similar. Now, you could probably go and make a more ADL native version of this, and I certainly invite anybody to do that. I take pull requests all the time on this repo, and that's linked in the description. And if you can come up with a better ADL version of this, I'd really love to see it. But anyway, that's what we're going to be doing is a lot of this stuff where we're doing pushes and pops for 16 bits, doing additions at 16 bits so that the carries still work, and we're not losing carry bits into these upper bytes of these registers. And then we'll look here at that fixed point library, and we have to do the same sort of thing, these little sacrificial bytes there for our words. and then things are still mostly the same, but again, we have to do a lot of .s's in there so that we are keeping these registers at 16 bits instead of 24 bits. It ultimately all works. And now we're going to see not just how the Agon compares to the Commander X16 in assembly language, but how the two different instruction set architectures that can run natively on the Agon on just the one main microcontroller. Of course, there's a whole nother microcontroller on there that we could do this for, but it's not 8-bit, it's a 32-bit, which is kind of the little cheating part of the Agon. We're sticking here still to the 8-bit, and even in ADL mode, it's still an 8-bit processor because it's still dealing with an 8-bit data bus in here. We just have two different widths of addressing. But anyway, yeah, let's take a look at how all these different demos run together. All right, now back here on the retro desk again, we have the two machines up and running. Over here on the Agon, We've loaded up that MZ80.bin. That's the mostly running in Z80 compatibility mode version. And up here we got man.prg, which is the assembly version of the same thing. So we are going to do run on both of these and all at once and go. Again, pregnant pause at the beginning, but it catches up real quick with the Agon. So that really, at just over a second, about a second and a half, we're able to get the full plot of the Agon up. And most of that second and a half is waiting for that first pixel, or rather the first solid character to come up. And over here, we're more in that same sort of 7-second range. So definitely a lot faster on the Agon for this. Now, let's try the ADL version. There, I can load MEZ80.bin and I'll run that. And pregnant pause, but there again, it's still pretty much the same. There ends up not being any performance boost going in ADL mode because the program it just takes longer to fetch. All of these special ADL instructions have these extra bytes to their opcode, so we're spending all this time fetching all these things and just doing all these things unnecessarily with more data than we need. So as it is, running similar code to the Z80, no benefit, especially for something like this where we don't have a need for more than 64K of memory. This is such a simple application, it doesn't really help us to use ADL at all. So where's leave us? And now why is the Agon so much faster? And I think also, why do some people point to this very benchmark as a mark of superiority of the Agon over the X16? Well, here's the thing. The fix, of course, is in the whole time for the Agon. And we're going to take a look at how once we go beyond this, things are going to be a little different. Some of the videos that we did later in the 8-Bit Battle Royale are showing some of the more advanced features of the Commander X16 that go beyond what the legacy 8-bit computers could do and what some of these new modern retro machines can do, especially with more advanced graphics. Now, of course, with the Commander X16, we have an 8 megahertz 6.5 CO2, so it's already going to be a lot faster at its core. And it has the on paper capability of being 640 by 40 pixels at 256 colors. But we can't really do that as a full-on bitmap in that mode because we're limited to less than 128K of VRAM. We have that 128K address space for the video RAM, but some of it's not actually used for video RAM, it's used for some of the registers, so we lose a bit there at the end, and so it's not enough to fully populate a 640 by 480 using the 8-bit color. But we can do that at 320 by 240, no problem. That takes a lot less VRAM, and from the experiments that I had done earlier in the series, it seemed that 48 maximum iterations was the sweet spot for this resolution, where you're getting a lot of information and there's you don't hit those diminishing returns yet when you do the higher levels of iterations, because when you have a low resolution, there's no point in doing thousands of iterations. It's not going to look any significantly different than 48 in this case. So the demo for the picture you see here, using BASIC, it took 1 hour and 12 minutes. It takes a very, very long time. But then there's the assembly language version, and using a special library that's a 16.8 fixed point, so it's using 24-bit values. Hey, easy 80. It can do that in 12 minutes and 8 seconds. It still takes a long time. Now, How would the Agon be able to do this? Well, that's a really good question, because we got to talk a little bit about how Agon does graphics. What we've seen so far in this series on everything that I've done in the Agon has all been in text mode. I have not shown the graphics mode because there's some issues with the way the Agon does graphics, because really the Agon doesn't have direct graphical access like the Commander X16 does with Vera, or the way that other legacy 8-bit computers have. It does everything as if it were attached to a terminal, and it just has that UART to this ESP32, and the ESP32 is a microcontroller running a piece of software, and that software is called VDP, and VDP is a FabGL application. As we'd seen with the TTGO VGA32, you can do a lot of cool things with FabGL, but what they've done for Agon is create something that's really optimized for text. So Agon's really great at text-based applications. Folks are making CPM work for it, and it's brilliant at that. We've seen how we can run Nano and the assembler on there, and Agon does a real bang-up job with that. And it just can't quite get its graphical act together. Now, it does have the capability to do 64 colors at 320 by 240, but it's not like a palette of 64 colors in this big color space. It is 64 colors, period, because we're dealing with 6-bit color as opposed to, say, 12-bit color on the Commander X16. And to have access to the 64 colors, you have to get into this 320 by 240 mode. And unlike pretty much any other 8-bit computer that has a bitmap mode, like the Commodore 64 or the Commander X16 or the Apple II or whatever, you don't have access to the whole screen as a big bitmap. What you have to do is split everything up into a bunch of bitmaps, and you have to holistically update each of those bitmaps. So say you have it your screen split up into like 16 by 16 bitmaps. If you need to change one pixel in that 16 by 16 bitmap portion, you got to update all 64 pixels in that bitmap. And it's not just like 4 bits within there, it's 4 full bytes that need to be changed. And so, yeah, it's a big drag on the system when you have to go through and do these updates. So updating a big bitmap like that for each time you go through, it's basically going to have to reload everything. So pretty much you're not going to be able to watch the bitmap load up. If you want to be as efficient as possible, you're going to have to sort of write it to memory and then do a load, and then that load is going to take a long time, and it might not even work correctly. I'm having a lot of difficulty getting a lot of bitmaps to appear on the Agon. And you also don't have a tile map. All the bitmaps and the sprites, it's kind of not a real big difference between them. They are all arbitrarily placed. So I draw a bitmap here, I draw a bitmap there. It's not like any sort of tile-based system where you can just say, here's my tile map and here's all my tiles, and I'm gonna place them in this order. That's just not a thing. And so again, you're dealing with having to just pump a lot of data through that serial connection. And so what beyond being optimized for text, for the Agon to do graphics, it's really set up to do vector drawing, because at that point it's the ESP32 doing all the drawing. All you're doing is on the EZ80 is setting up some coordinates, pushing them over the serial link and saying, all right, well, you go ahead and draw a line from here to there, and then the ESP32 does it. And of course it does it very quickly because it's a very fast 32-bit processor. And so, yeah, if you may actually, at that point, if you're just going to have the ESP32 do all your heavy lifting for drawing, you might as well have the ESP32 do the actual Mandelbrot calculation as well. And so that's something I think I'm going to do at some point, but then it's no longer an 8-bit battle royale. That's a 32-bit battle royale. And I'd be writing that in the Arduino programming language for FabGL. But then we'd have the difference between the Agon and, say, the TTGO VGA32, which is just like a $12 little mini, little itty bitty type computer. And yeah, so yeah, you could get even faster possibly, because this is a higher end ESP32 than it comes on the Agon. So who knows? We'll see what happens down the road as we try to make more things happen. But that the 16.8 fixed mode, maybe ADL will be able to do that, doing some fancy 24-bit math, making things a little faster. Who knows? We'll see what happens. But you're not going to be able to perform in exactly the same way, and we're going to start seeing some diminished returns once we do things that can't just be done in text mode on the Agon. So let's take a look now at our final leaderboards for the 8-bit Battle Royale. Now at the top of this, having a real easy 80 processor, is the Agon Light 2 at 6 seconds using BBC Basic. So you can see just how much faster it is. Pretty much the exact same program running on a BBC Micro takes 1 minute and 37 seconds. So if you really like BBC Basic, the Agon Light is going to really be a very efficient platform for you. It's going to get those kind of programs really running quickly. And of course, Commander X16 takes about 23 seconds. And so, of course, that's a lot faster than, say, Commodore 64 at 3 minutes and 23 seconds. So it all depends, I think, really on the type of programming environment you want to do, and sort of the things that you would want to do beyond a benchmark like this, that if you're going to want to make like a really graphically and sonically rich game, the Commander X16 is going to be the real obvious choice for doing that. And there's a fully featured emulator where you can just do that for free without having to buy some of this more expensive early hardware. Even though the later generations are going to be cheaper once they're no longer a through hole, and then eventually shrunk down to a single FPGA or ASIC type implementation. For the Agon, things are working great on text mode. Hopefully things get better on the graphics front. It's still very much a work in progress, so we'll see how that evolves as we go on there. But now, finally, for assembly, Agon Light 2 at a blazing fast 1.5 seconds. It is twice as fast as the Commander X16, regardless of the addressing mode that you're using. Now it is 18 megahertz versus 8 megahertz for Commander 16. So what we're seeing now is that the Easy 80 is starting to is now catching up to the 6502 in terms of cycle efficiency, whereas before the original Z80, it would take about twice as many cycles to do the same amount of calculations that the 6502 could do in a lot of cases. And so that's why we saw things like the BBC Micro being slightly faster than the Amstrad CPC, even though the Amstrad CPC ran a Z80 at 4 megahertz versus a 2 megahertz 6502 in the BBC Micro, because the 6502 is about twice as fast. That's no longer the case. You don't have that sort of cycle performance advantage with the 65CO2 versus an EZ80. So if we were able to get a 65CO2 based computer running up at 14 megahertz, which is the theoretical, or at least not really theoretical, that's the listed limit, but I bet you could probably make it work at 18, but you know, your results may vary. It's not guaranteed to do that. That maybe we would be able to get up to that Agon level of performance with a 6502 based system. So anyway, that's where we're at with 8-bit Battle Royale, and I think we're going to see a few more things that we can try, especially as the Agon evolves and we have maybe some more efficient ways of being able to deal with the graphics. So thanks for watching, but thanks especially to the people that really make what we do here possible, and that is our patrons. And here they are. These folks have been sticking with this channel a long time for a lot of these folks, and all through the different changes and renames and repurposings, and I think we're doing some even more interesting stuff right now and getting down to the real brass tacks of pitting hardware against each other and doing real live demos with some of these systems that, like Commander X16, have just been theoretical for a long time. And now we have the Agon as another thing to play with and to see some of the real differences in there and really cross purposes of these two different machines, two very different approaches, two very different user experiences for retro machines. So, but if you want to see more of this and you want to see it without all the ad business you might have seen earlier, hit us up on Patreon. You get to see all of my videos ad-free before they come out to the general public. But if you don't want to do that, it is completely 100% absolutely free to subscribe on YouTube and click that bell to be notified as soon as the videos go out to that general public. And then I hope to see you when that next video comes out, and we'll do some more awesome stuff right here on the Retro Desk. All right, take care. Bye-bye.